Yes. 23. Ah. I feel like this is going to segue us into a mini lesson because I think it's something we have not covered yet. 23. Yes, it's going to segue us into a mini lesson. Woohoo! Okay. So you will want some paper. All right. And we're going to talk about standards. So make sure you've got yourself some paper of some kind or other. What is a standard solution? It is a solution, and you would use it to titrate something because you know what about it? Yeah, it is a solution of known concentration. Now, there are certain substances that you can just make a solution and you can know its concentration. Those are called primary standards. And I don't know if you remember, but the little shortcut for primary looks like that. Okay, little primary. A primary standard is a solution made from a pure non-hygroscopic and what the heck is hygroscopic? Hygroscopic is water absorbing. I guess I should put in here, it is a standard solution made from a pure non-hygroscopic crystalline solution. And the reason it's called a primary standard is because these characteristics allow you to just measure out the mass and know how many moles you are getting. Okay? And I'm going to give you an example of something that can be used as a primary standard and an example of something that can not be used as a primary standard. So, for example, oxalic acid dihydrate is a pure non-hygroscopic crystalline solid. So when you measure out 10 grams of this substance, you know that you got 10 grams of that. So here we have our 10 grams. And it is all. Actually, could you guys write the formula for oxalic acid dihydrate? If you don't know the formula, you can look on your acid chart. What is the formula for oxalic acid? H2C2O4. Now, when we add that ending dihydrate onto it, what does that mean? We add two H2Os. And how do we write that in the formula? We put a dot and then we put two H2O. And do you remember where those waters are? They're embedded in the spaces in the crystal lattice. Yes. No, because it hydrates to a specific amount and it stays there and it's consistent. It's always 2 H2O. It's never 1 H2O or 3 H2Os or just some random amount. Okay? Okay, so there's specifically 2 waters for every 1 H2C2O4, not a random quantity, which is what you would get if something absorbs water. Okay? And because oxalic acid has these properties, it is a good primary standard. You're going to know how many moles you have in how many grams because it is pure. Now, if we have instead some sodium hydroxide, it absorbs, does it also absorb carbon dioxide? It at least absorbs water and possibly carbon dioxide from the atmosphere. So I'm just going to say water for now. So actually, if you look at sodium hydroxide, it usually comes in little pellets. Okay, they're about the size of maybe like a half a pencil eraser. Okay, they're about that size. And they kind of look shiny and they're a little bit gooey on the outside. Like if you poke at them, you're like, oh, a little bit gooey. And that's because they are absorbing water from the atmosphere. So if you take 10 grams of sodium hydroxide, and you'll notice I put it in quotes here because this part over here is NaOH. Okay, and this part is water, right? So we have 10 minus X grams of NaOH because we just weighed out 10 grams, but some of those 10 grams are water. And we don't know how much because it doesn't do it in any sort of specific ratio. So could we figure out exactly how many moles of NaOH we have from the mass? No, because some of that is water. So what we could do is we could take this and we could prepare an approximately 0.1 molar solution of NaOH. But is it going to be exactly 0.1 molar? No, because we don't know exactly how much. So what we would need to do is we would need to take a primary standard like a solution of oxalic acid and use it to titrate the NaOH until we finally know the concentration of the NaOH. So what we can do is prepare a primary. Remember that little symbol means primary. Standard. Say 0.05 molar. Nope. Sorry. 0.0500 molar H2 C2O4. (100 milliliters). And we can titrate, and we use it to titrate the NaOH. This allows us to find the concentration of the NaOH, which means we have standardized the NaOH because then the concentration will be known. Yes?
Is it better to use titrate of
It just depends on what you're trying to do. So in general, what we want is we want volumes of the titrant used to be not too big, but not too small. Like you don't want your volume of titrant used to be greater than 50 milliliters because that means you're going to run out of, liquid in your burette. Yes? You don't want it to be too small, like say under 10 milliliters, because now you're limiting yourself to 3 significant figures instead of 4 significant figures. So it's kind of nice to have something between sort of minimum 10 milliliters and maybe around 25 milliliters, something like that. Okay, so we often will be titrating where we end up with volume somewhere between 10 and 25 milliliters. Yeah? And if my NaOH was 0.1 molar, my H2C2O4, that's going to be a 1:2 ratio, right? I'm going to have one of these. Let's just write the equation. H2C2O4 plus NaOH. What do we get? Many people want to say NaHC2O4 because we know that that second hydrogen only dissociates a very little bit, yes? But are we writing a dissociation equation? No. We are writing a neutralization. And this is not a two-way arrow. This is a one-way arrow. I'll show you the equilibrium in a moment just to prove that it happens this way, but NaOH drives this reaction to completion, which means it's going to rip both of the hydrogens off of the H2C2O4. This strong base drives the reaction to completion. It rips both H pluses off H2C2O4. So what should our product be here? Na2C2O4 plus H2O. And because we have 2 hydrogens, how many hydroxides do we need? 2. How many waters will that give us? 2. And so that is our balanced equation. So if we have, it's kind of nice when you're doing a titration to have similar concentration of what you are titrating, the analyte, and a similar concentration of the titrant. And because this is 2:1, we're going to make this concentration about half of what the sodium hydroxide concentration will be. Does that make some kind of sense? Yeah? Okay. Okay, so we prepare our primary standard, say this 0.05 molar, and we're going to make 100 milliliters of it. And the reason I mention 100 milliliters is that I'm going to have you describe how to make this in a moment. And we're going to use it to titrate the NaOH. This allows us to find the concentration of NaOH precisely. This process where we take our primary standard and we titrate the one where we kind of know the concentration, but not really, this process is called standardization. Because we are finding the concentration. Now the concentration of NaOH is going to be known. And remember, a standard is a known. Yes? Standardized. Oh, I left out a whole syllable there. standardization. Because, I don't know why that's two words, then we will know the actual concentration of the NaOH, and standard means that the concentration is known. At that point, we will say that the NaOH has been standardized. So, you guys right now are going to do the calculations and outline the procedure that you would use to make this solution. And you're going to keep it somewhere where you won't lose it, because this is going to be part of the lab that you do in January. Okay? So, do the calculations and outline the procedure to make a primary standard, in this case, 0.0500 molar H2C2O4, 100 milliliters, starting with solid oxalic acid dihydrate. And let's call that 100.0. So we have some sig figs. What do you need to calculate first? Thank you. Now you need to be careful when you get to step 2, because if you find the moles of H2C2O4, that's great, but you're starting with oxalic acid dihydrate. So when you go to calculate the grams, your molar mass should include what? The 2 waters. Okay? So you could also say that this is also equal to 0.00500 moles of H2C2O4 dot to H2O, and you will include that water in your mass when you do the mass calculation. Are you guys good with 0.63 grams? Did I do it correctly? Okay. Now you have to figure out what are you going to do with those 0.63 grams. Let's assume I put my little beaker on a scale. Yes. And I've weighed out 0.63 grams. So our procedure have a chat with your neighbor. What next? Got a little pantomime going on in the back there. All right, so what are we going to do with this? We want to make a solution. I know my back row there knows what they're doing. At least that part of it, I don't know. Do you guys know? We have to burn the water out of it. No, we do not. Because what's going to happen is when it dissolves, the water is just going to be set free, right? Because the ions will separate, and then the water that was inside the crystal will just float free along with the ions. Okay? This is the kind of thing they love to ask about on the AP exam. They're like, oh, here's some equipment. What would you do? Measure out 100 milliliters. Okay. Like that? Okay, now what? Yes. Ooh, you guys are not as much fun as my other block. I got to play with them a lot more. They were like, okay, put it in a flask. And I was like, okay, put it in a flask. And then they were unhappy with this flask. And they said, what volume is it? And I said, 500. And they said, oh, that's too big. And then I said, oh, so what size do we need? And they said 100. So I said, oh, okay. And then they said, oh, no. And then somebody's like they're like this and the skinny one. And then they, oh, but you know the name. What's it called? Volumetric flask. Okay. What size do we want? 100 milliliters, because we're making 100 milliliters of solution. Why is it called a volumetric flask? Because it measures only one volume. So you need to make sure that volume is whatever volume you want to make. There's just one line right there. That's our calibration line. So we're going to put it in there. Now, I've just been, lackadaisically throwing this from one to another. If I do this, I feel like I'm going to spill. Yes, seems likely. What should I do to prevent that spillage? Use a funnel. Okay, we have two choices of funnel. Which one? Skinny or fat? Skinny, okay. Oh. What happened? I could shake it a bit, but that's because I happen to have just a very, very small, okay? Normally, we will not use this kind of funnel because the solid could get stuck. It is better practice if you have a solid to use a powder funnel. Now, because we are a high school and some of our equipment is a little bit ghetto, this doesn't actually fit here, okay? But what you can do is you can approximate it just by putting it on like that and folding it there, okay? Anyway, so then we would transfer it into there. So step number 2, transfer. The solid into a 100 milliliter volumetric flask via a funnel. Powder funnel. What next? Burette? What am I going to do with your burette? No, okay, no burette. Okay. Okay, why am I filling the flask 2/3 of the way? Why am I not filling it all the way? Yeah, what I'm going to do is I actually have another flask here, and I'm going to, without putting any solute in it, I'm just going to show you what it looks like when I try to stir it when it is filled to the line. I don't have enough water, do I? No, I don't. Okay. So if I fill this to the line, and I'm not going to be very careful about this, I'm just sort of throwing it in. How much mixing am I getting? Not very much, okay? So in order to avoid that, you're absolutely right. We fill it about a half or 2/3 full, the water, and then what do we call this process? Swirling. We are swirling. So we swirl to dissolve the solid, okay? And then once we have dissolved the solid, let's see, is it all gone? Not quite. Now it's all gone. What do I do next? I fill it the rest of the way. La 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 la. Oh no, I went past the line. Oh no, what do I have to do? Start over again. Okay, if you go past the line, you have to start over again. Let's pretend I did not go past the line. Okay? How do I avoid that problem? I'm going to, sorry? I'm going to use a dropper. Yes, absolutely. Okay, so I'm going to add water. And then once I get to a certain point, the dropper, I had a dropper up here somewhere. Oh, there it is. Okay, and when I get to a certain point, I'm simply going to add water with a dropper. And then when I start to get really close, do I hold it like this? Why not? I can't see the meniscus. Should I hold it like this? No. Where should I put it? I should put it on the desk, right? And where should I put my eye? Right at eye level, okay? So I get my eye down there, and is it the top or the bottom of the meniscus that I want at the line? Bottom of the meniscus. Okay, there it is. Great, done. Am I done? No, what do I have to do? But I need to put a stopper. Excellent. Oh, I'm so disappointed. You guys are no fun. My other class was like, flip it. And I was like, am I going to flip it? Flip it? That sounds like fun. I can barely catch the pen. Imagine me trying to catch this. Okay, so yeah, you're absolutely right. We do not flip it. We invert it to make sure our solution gets fully mixed. Excellent. Okay, so could you write the rest of that procedure so it is, once again, in your brain a little better? And then after Christmas, we're going to actually have you do it. Okay, so keep that number, that 0.63 grams, because that's how much you're going to need to make of the oxalic acid, okay, when we come to your lab in January. So, and then once you have this, you can titrate your NaOH. And actually, what we will end up doing is this is one of the few instances where we will actually put our unknown in our standard will go in the flask, and our NaOH will go in the burette, because we want the NaOH to be in the burette for the next stage, which is to titrate an acid with the now standardized NaOH. So you would then, voila! We have a primary standard. I don't know why I did not manage to get this into your workbook. I was supposed to. I had like a little written out thing like this from last time, and it's a file in my thing, and it just never made it into the workbook. So, oh well. It wasn't that big of a thing. So, it'll make it into the next edition. So that takes us then to question 23, which at this point should probably be pretty straightforward. Which of the following explains why oxalic acid is useful as a primary standard in acid-base titrations? Is it because it has 2 replaceable hydrogen ions? No. Is it because it can be obtained very pure and is a crystalline solid? Yes. Is it because it has a large Ka and so it gives better results? No. Yes?
Why does it need to be crystalline?
It just makes it easy to weigh out. Lots of acids come as concentrates. So if I go and I get some HCl, I do not get a solid HCl, because at room temperature, hydrochloric acid is actually a gas. Okay, so what happens is I get concentrated HCl, and then I have to dilute it. And so it's not going to be as precise as I can get with a crystalline solid. Yeah? And it is not because the stoichiometric point in titrations is on the basic side of neutral. That just, I don't even know what that's talking about. Okay? Other questions from the review? Yes? Could you have the review? Yes? Anyone else need a copy? Anyone else? I guess I should also ask, is there anyone is either done this review or just would like at this point a copy of the extra AP-based review? Wait till tomorrow? You'll get one? Okay. Anybody else want one today? No, okay, there you go. So we're good? Alrighty then. last day when we left off, we were going to start choosing an indicator for an acid-base titration, but we didn't quite get there. Okay. So this is on page, I believe, 106. Yes. So in this particular instance, we are titrating a strong acid with a strong base, which means that the pH at the equivalence point will be yeah. Why is that? There's no hydrolysis of the salt. Okay. Now, if we go to our table of acid-base indicators, we might look at that and say pH 7. Well, bromthymol blue looks like it kind of changes around pH 7, yes? That would be a good choice. But it turns out we have a lot more options than just bromthymol blue, which is fortunate because bromthymol blue changes from yellow to blue, which means that your end point or your transition point, what color will it be? Green. What specific shade of green will it be? Exactly. I got a shrug over here. What specific shade of green will it be? That's a little hard to tell. Yes? Wouldn't it be nice if we had something where we could tell when we just got to our transition point? What did we use last year when we did a titration that just allowed us to see us just reaching our transition point? It was really quite easy to see. We used phenolphthalein. And the reason we used phenolphthalein is because it goes from colorless to pink. So the moment you see that pink color staying around, you know that you are at the end point of that indicator. Yes? Now, let's look though at phenolphthalein. Phenolphthalein changes color from pH 8.2 to 10.0. So it is really transitioning at about a pH of 9. So why is it still okay to use phenolphthalein for the strong acid, strong base that we did last year? Let's go back. How much difference in volume is there between pH 7 and pH 9? How much difference in volume of NaOH added? Like none, okay? And in fact, even if we go down to like pH 4, there is really no difference in volume. And if that is the case, That means that that phenolphthalein will change when we get to the equivalence point. The equivalence point is at 25 milliliters. And it takes us 25 milliliters to get to the equivalence point. It takes us 25 milliliters to hit the pH 4. It takes us 25 milliliters to hit pH 7. It takes us 25 milliliters to hit pH 9. So any of those will indicate that we have hit the equivalence point. Yes? Because that vertical section is so steep and so vertical and so long. Okay, so we can use any of these indicators are okay to use for this titration because they will change color at 25 mils of NaOH added. Yes.
Say that
Sorry?
say that it, you could probably say that, like, as soon as it starts indicating that it.
Yeah, you can. I will say I have done titrations where you needed to decide when it turned from muddy brown to muddy green, and it was frustrating as all heck. Plus, it was more frustrating because my professor that I had for that course, he was a jackass. I would go up and I'd be like, is this the color I want? And he'd be like, I don't know, you tell me. And I was like, well, I've never done this before. And this was before, like, there was no internet. I mean, there was email, right? But you couldn't look anything up online. There was certainly no pictures of anything online. You might be able to go find a book in the library with a reference photo if you were lucky, but you weren't doing that in the middle of a lab. So anyway, I really hated him. His name was Professor and I was like, I hate him. I just hate him. It was like HAIGHT or something like that. And I'm like, what an appropriately named professor. Because he was a jerk. Anyway, I will say that when you have the easier it is to see a transition point, the better anytime, right? Because you're like, did it turn green or is it still blue? Right? Do you know what I mean? Like it is harder to see. So that's why we generally tend to use phenolphthalein when it is an appropriate indicator. Yes?
If you needed to be like really, really specific, whatever reason, you could use it.
You could, but even easier than that would be a pH meter. Yeah? So we can use any one of these to indicate the equivalence point. Because their endpoint, the endpoint and the equivalence point coincide. They occur at the same volume. So when you go to choose an indicator, you want the endpoint to occur at the same volume as the equivalence point. That's not going to be the case for every single indicator, as we will see in just a moment. Because if we go down to here, which of these indicators, we have alizarin yellow, phenolphthalein, bromthymol blue, bromphenol blue, and methyl violet, which of these could we use and which would be a good choice? Which ones would change color at the equivalence point? Which ones can we say for sure yes? Bromthymol blue, yes. Phenolphthalein, yes. I feel like bromphenol blue, yes, I think. I also feel like alizarin yellow, maybe. Bromphenol blue, I feel like it's also kind of maybe. But why would you choose those when you could choose something that is definitely within the vertical section? You know what I mean? So these would be the best choices. What about methyl violet? No, because methyl violet changes at a pH of, let's see, methyl violet changes at 0.0 to 1.6. So the transition point is 0.8, which is like here, right? You're like, so it's changing at about, what, 13 milliliters or so? How about orange 4? Try orange 4. Orange 4, ivy. Orange ivy. At what color, at what pH range does methyl 4 change? Yeah, 1.4 to 2.8. I don't know what I'm writing here. 1.4 to 2.8, and the average of that is 2.4? 2.1. So 2.1, we go across and we say, 2.1 is going to happen at about, I don't know, what does that look like? 18 or 19 milliliters? 19 milliliters? Is that what we want?
Yes.
Is it? No, it's too soon. We want it to change at 20 milliliters, and it is not changing at 20 milliliters. So orange 4 is a no. Is good? Could you find another indicator on your table that would definitely not work? Thymol blue. I heard, but wait. Thymol blue. Thymol blue. Thymol blue is a little of a weird one. Yeah. Why is thymol blue weird? It has 2 transition points, yes? So if you look on your table, thymol blue is both here and here. So although it will change from red to yellow, you don't need to worry about that. You would just look for it to turn from yellow to blue, and that would fall within the vertical section. Yes? Okay. Do you guys know what that means about thymol blue? What kind of an acid it is? It is a diprotic acid. Okay, yeah. We would have H2 IND in equilibrium with H plus H IND minus in equilibrium with H plus IND 2 minus, and this would be red, this would be yellow, and this would be blue. Yes? Okay. Is there another indicator which would not work for a strong titration? Indigo carmine. Indigo carmine changes at pH 11.4 to 13.0. So that's going to be in the neighborhood of 12-ish, 12.2. So that would be about here, right? And that is not 20 milliliters. No. So when you have a strong, there's going to be a plethora of indicators that you could choose from. Do you guys know the word plethora? A lot. There is an abundance of indicators. Okay, a ton of them. I like that word. So basically, the point in a titration where the indicator changes color is called the end point. So the end point is the point in a titration where the indicator changes color. What is the equivalence point again? I'm going to say rather than moles of acid equal moles of base, I'm going to say moles of H are equal to moles of OH, because what if you had, say, SrOH2 and HCl, then your moles of acid wouldn't equal your moles of base, like, or at least the language becomes a little dodgy, if you know what I mean. What is another way of saying that? Yeah, the stoichiometry is perfectly fulfilled. Which leads us to the fact that there is another word for the equivalence point. Does anyone know what it is? The stoichiometric point. So if you hear the word stoichiometric point, it just means equivalence point. Okay, the graphs below show the titration of a weak acid with a strong base. So weak acid, strong base. For each of the graphs, we're going to write down the volume of NaOA needed to reach the equivalence point. And based on whatever indicator you have, so for this first one, it's going to be phenolphthalein. Blah. For this first one, it's going to be phenolphthalein, and for the second one, it's going to be methyl red. What was the volume of NaOH needed to reach the end point? So do that for both of them. So volume of NaOH needed to reach the equivalence point, and then the volume of NaOH needed to reach the end point for the selected indicator. Okay, volume of NaOH required to reach the equivalence point is 50. Why am I writing 20? What's wrong with me? 50 milliliters. And for our first one with the phenolphthalein, the volume of NaOH needed to reach the end point is 50 milliliters. Is phenolphthalein an appropriate indicator? Yes. All right, in our second one, volume to reach the equivalence point is 50. Volume to reach the end point, 35, or something close to that anyway, 35 milliliters. Would methyl red be an appropriate indicator for a strong base weak acid titration? No. Okay. We feel good about that? Then there's some exercises at the end. I'll let you do those on your own. Hang on here. Oh, actually, why does that say 10% purity? I don't know. We have 10 more minutes. Do you want to do metal, non-metal, and metalloid oxides? No? I got one no, I got one sure. Okay. Metal, non-metal, and metalloid oxides, page 111. And this will take us through everything that will be on your test, and then we'll be into acid extras for AP. Extras for AP. Woo. Okay. So metal oxides act as bases. Ooh, this needs fixing. Because this is supposed to point here, and this is supposed to point here. So these need to all move over a little bit. So if you recall, O2 minus is a, what kind of a thing is O2 minus? Strong base. So if you have a soluble metal oxide, which most group 1 and 2 metal oxides are, you're going to release O2 minus, and O2 minus will undergo hydrolysis. And it's going to undergo 100% hydrolysis because O2 minus is a strong Bronsted-Lowry base. And what do we get when we have that hydrolysis reaction happen? OH minus plus OH minus. Okay, could you please show how barium oxide produces hydroxide in solution? Start with the dissociation equation. Okay, you can write OH minus plus OH minus, or you can just write 2OH, either is fine. But generally what we do is we take these two steps, step 1, step 2, and we combine them into barium oxide plus water gives barium hydroxide. Sodium oxide plus water gives sodium hydroxide. So basically what you have is that you have the metal oxide plus water, and that's going to give you the metal hydroxide. And then you would just need to balance it. And mostly for the regular exam, you just need to know that metal oxides are basic and be able to write the equation. And that's virtually it. Yes?
So, is acid rain?
Acid rain is due to non-metal oxides. Sorry, you asked acid rain, is it not?
Is that the scope or is that?
No, acid rain is on our regular test. Yeah, but it is related to this topic because it is due to non-metal oxides. Okay? So, could you please write the balanced formula equation for the overall reactions of calcium oxide and lithium oxide with water? Yeah, and then we would need to balance it. Oh, that's why it's not going to balance, because I didn't write the correct formula for lithium. Ha ha ha. Silly me. There we go. One, two, 1, 2. Yeah, okay. I can count. Sure I can. So your homework at this point, I don't think there's really any point in carrying on right this second. Your homework is to do the previous thing. Where is it? Choosing this. Page 108, 109. And you should also finish the acid base 2 review. There will be a quiz tomorrow, but remember it is a practice take-home quiz. Okay, so if you're like, there will be a practice take-home quiz on buffers and titration tomorrow. Is good? Okay, very nice, very nice.